Hello everyone, and welcome to our session on diamond manufacturing technology and skills. My name is Liang Wei Zhang, and during this session, we'll follow a rough diamond through the traditional workshop flow: planning, preparation, dividing, shaping, facetting, and polishing. Today is deliberately hands-on and old school. We'll focus on the practical judgment and bench skills that make the whole process reliable and repeatable. Here's how we'll structure the class. Part 1 is about reading the rough and planning in a traditional way. How you decide what's possible, what's risky, and what's worth doing. Part 2 covers bench preparation, the tools, windowing, marking, and doping. Basically, how you set yourself up for accuracy. Part 3 is dividing, cleaving and conventional blade sawing, with the common failures and how to avoid them. Part 4 is shaping, table smoothing, bruting, girdle control, and managing naturals. Part 5 is faceting and polishing on the scathe, including polishing grain and directionality. Let's begin with Part 1, from rough to plan. This is where most of the value is either protected or accidentally destroyed. In a traditional workshop, planning isn't software-driven. It's observation, experience, and a disciplined routine. If you plan well, the later steps feel straightforward. If you plan badly, every later step becomes damage control. So, as we go through this section, keep one idea in mind. A good plan is not a dream of a perfect stone. It's a plan you can actually execute safely with the tools and time you truly have. When we say manufacturing in a diamond workshop, we're not talking about mass production. We're talking about a sequence of controlled decisions. Every decision balances three things: yield, quality risk, and shape. Yield is weight retention. Quality risk is mainly inclusions, stress, and edge damage. And shape is what the market or design wants. Traditional skill is the ability to make these trade-offs early, before you remove material you can't put back. So manufacturing is really about risk management with your hands. Deciding where you can be bold, where you must be cautious, and where you should simply stop and recheck. Traditional manufacturing starts even before cutting, at the mindset level. Strategic planning means you don't just ask, "What can I cut?" You ask, "What should I cut for the best outcome?" Then comes purchasing logic. Different rough crystals look similar until you notice the features that will create losses or limit shape. Finally, tracking is the quiet discipline that prevents expensive mistakes. You record identity, weight, visible features, and decisions at each stage. In many workshops, it's simple: a paper card, a stone parcel, a bench log. The point is consistency, so the stone never becomes mystery rough halfway through the job. Let's talk about rough types, because shape tells you a lot before you see anything inside. A classic octahedral roof often offers clearer options for orientation and splitting decisions. A mako, or flattened twin form, can constrain your choices and influence whether cleaving is sensible. Broken crystals and irregular pieces can still yield great stones, but they demand more careful planning because reference planes are harder to establish. The practical point is this: before you fall in love with a final shape, ask what the rough naturally wants to do. Traditional cutters respect the crystal. They don't fight it unless the value clearly justifies the risk and the loss. Planning without advanced systems is absolutely possible, but it requires a method. First, decide the target outcome: one main stone, a pair, or multiple smaller stones. Next, sketch the rough in simple lines. Top view and side view is usually enough. Then mark likely risk zones, obvious inclusions, feathers, or strained areas you suspect from the way light behaves. Finally, place the future girdle and table in your mind. You're not chasing perfect proportions at this stage. You're choosing a workable orientation. The key skill is translating an idea into actions. Where will I split? Where will I grind a window? Where will I create a stable reference face? Traditional observation is your best friend. With a loupe or microscope, you're not only identifying inclusions, you're reading their position and direction. A crystal in the middle behaves differently from a feather near the edge. Look for features that could propagate during splitting or create chipping during shaping. For stress, a simple traditional approach is careful observation under changing angles and lighting. If you have polarizing equipment, it can help reveal strain patterns, but even without it, unusual tension signs often show up as odd reflections and unpredictable surfaces. The practical habit is this: don't just describe the inclusion, decide what it means for your next move. Shape matters because it controls how much you must remove to reach a clean, symmetrical outline. If the rough already suggests a rounded volume, yield for a round brilliance may be more favorable. If the rough is elongated, a fancy shape might protect weight. In traditional planning, I like to think in three drawings: the rough outline, the intended outline, and the post-splitting outline. That third sketch is where you either save weight or lose it. Remember, you don't need a perfect drawing, just enough to stop yourself making a beautiful plan that's physically impossible. The best planners are not the most imaginative. They are the most realistic. Inclusions are not only about how many, they're about where they end up. If an inclusion sits near the center, you should assume it will be visible unless you deliberately place it under an area that reduces its impact, or you redesign the stone so it's removed. If inclusions sit near the edge, you may be able to position them into the girdles area or into junctions where they are less noticeable. But you must be careful. Edges are where chipping happens. Traditional placement tactics are a kind of choreography. You're deciding what the customer will see face up, what the setter will notice at the girdle, and what might become a durability issue 5 years later. That's planning, not polishing. Color can be subtle, but orientation can change how it reads. A slight tint may appear stronger when the stone is viewed face up in certain orientations, especially if color is unevenly distributed. In traditional planning, you don't have fancy modeling. You have your eyes, your lighting, and your discipline. View the rough in consistent conditions, face up, side on, and through any window you create. Then decide where you want the viewer's attentions to go. Sometimes the best choice is not the highest yield, but the orientation that avoids concentrating color in the center. In other words, You're not only cutting a stone, you're designing how it will be perceived in normal wear. Now we move into part 2, tools and preparation. This section can feel mundane, but it's where accuracy is built. Traditional diamond work relies on repeatability. The same grip, the same checking routine, the same alignment habits. If your bench is messy, your stone will pick up scratches. If your doping is rushed, your symmetry will suffer later. So think of preparation as the quality system of a workshop, done by habits, not by machines. We cover bench safety, core hand tools, windowing and marking, and finally doping, which is the gateway to controlled cutting and polishing. Let's be practical. Diamond work produces fine debris and sharp fragments, and both can ruin a stone or hurt you. Keep the bench clean and don't let diamond powder or grit migrate to the wrong stage. Cross-contamination is a classic cause of random scratches. Eye protection is not optional. Even tiny chips are dangerous. Posture matters too. You need steadiness, not force. A traditional rule is slow hands, clear eyes. Also, build in micro pauses. Stop, breathe, recheck your alignment, and only then continue. Most mistakes happen when someone thinks, "I'll just finish this quickly." Diamonds punish that attitude, and they do it immediately. A traditional kit is simple, but each tool must be used consistently. You need reliable magnification, typically a 10x loupe, and ideally a microscope for tricky areas. You need good tweezers and stable holders, because dropping a rough stone is an avoidable tragedy. For marking, a permanent marker is common, and a scriber can help when you need a more definite line. For fixing, you'll use wax or adhesive system depending on workshop practice, plus a heat source for controlled softening. Add basic measuring tools and a log for weights and decisions. The real tool, though, is your routine. Observe, mark, check, and only then act. Windowing is a traditional way to reduce uncertainty. If the rough surface is frosted or irregular, you may not be able to judge inclusions or color properly. So you grind a small flat window, just enough to see inside. The key is restraint. A window is not shaping, it's information gathering. Choose the position carefully, because every bit of windowing costs weight. Once you have the window, recheck everything. Inclusions, any fader directions, and whether your earlier plan still makes sense. In good workshops, windowing often triggers a plan revision, and that's not failure, it's professionalism. You're paying a small weight cost to avoid a big mistake later. Marking is where your plan becomes a set of instructions the workshop can actually follow. Traditional marking may look simple, a few lines, but those lines have to carry meaning. You mark intended split lines, likely table position, and any "do not cut through here" risk zones. A good rule is mark as little as possible, but make it unambiguous. Think like a colleague who will handle your stone after lunch. Will they understand what you meant? Marking also forces clarity in your own thinking. If you can't confidently draw where the action should happen, you probably haven't decided yet. And if you haven't decided, you should not start removing material. Mark first. Cut second. Doping is a traditional skill that quietly controls everything that follows. You're fixing an irregular object to a dop so it behaves like a controlled, repeatable shape. The big idea is the axis. If the axis is off, symmetry problems appear later and are very hard to correct. With wax-based fixing, your job is to heat gently, align accurately, and let it set without movement. Don't rush the cooling phase. Tiny shifts matter. Also, plan for the reality that you may need to redope. Good workshops treat redoping as normal, not embarrassing. The goal is not pride, it's alignment. If the dope is right, the rest becomes possible. We now come to part 3, dividing. The moment where the rough becomes smaller pieces, you can truly control. Dividing is not glamorous, but it's high stakes. A good division creates clean surfaces and predictable geometry. A bad division creates cracks, unexpected losses, and sometimes a ruined plan. In traditional practice, you mainly choose between cleaving and conventional blade sawing. Each has its own logic, its own risks, and its own feel. As we go through this part, I want you to keep asking one question. Am I letting the diamond structure work with me, or am I forcing it to behave? So, when do you cleave and when do you saw? Cleaving can be excellent when you have a clear cleavage direction and you want a clean split with minimal loss. Sawing is generally chosen when you need more flexibility in where the split happens, or when the crystal form makes cleaving risky. The trade-off is straightforward. Cleaving is fast and low loss but unforgiving. Sawing is slower and creates curve loss, but you can steer it. Traditional skill is not being good at cleaving. It's making the right choice for this specific stone on this specific day with the risks you can actually manage. The best cutters know when not to be heroic. Cleaving works because diamond has directions where it splits more readily. Its crystal structure offers planes of weakness. In traditional teaching, you treat cleaving as a precision act, not a strength contest. You identify the likely cleavage direction, you create a controlled starting point, and you apply a decisive, aligned force so the split runs where you intend. The danger is that internal features, like feathers or strass, can divert the split. That's why cleaving begins with observation, not with tools. If you're uncertain about the internal state, cleaving becomes gambling, and in a workshop, gambling is expensive. The traditional mindset is, cleave only when the stone is speaking clearly about how it wants to separate. Traditional cleaving tools are simple, but each one has a job. The cleaving stick or holder keeps the stone stable and gives you control over orientation. Wax or a fixing medium holds the rough securely. If the stone shifts, your accuracy is gone. Then you create a small notch or groove as a starting point. This is where you tell the diamond where to begin. The cleaving blade is placed into that notch, aligned with the intended direction. Finally, the strike is applied, controlled and decisive. Notice what's missing. There's no need for repeated heavy blows. A good cleave is one clean action, supported by careful preparation. Your tools only work as well as your alignment and your patience. Here's a traditional cleaving sequence. First, fix the rough securely so it cannot rock or twist. Second, confirm direction again under magnification. Don't trust your memory. Third, cut a small notch at the intended start point. Keep it neat, not messy. Fourth, place the blade into the notch and align it carefully. Fifth, apply a single control strike. After the split, don't immediately celebrate. Inspect the new surfaces. Look for clean separation, unexpected chips, or signs that a crack continued beyond the split line. Traditional practice is to treat the inspection as part of the process, not an afterthought. If something looks wrong, stop and reassess. Don't carry on anyway, just to keep the workflow moving. Cleaving failures usually have predictable causes. If the split runs off plane, you likely misread direction or place the notch incorrectly. If the stone shatters or chips badly, stress or internal weaknesses may have been present, or the fixing was unstable and allowed movement on impact. Another common issue is a stepped or uneven cliff face, often caused by poor notch quality or blade misalignment. Prevention is traditional and boring. Check stress signs. Keep the notch clean. Ensure the stone is firmly held, and make the strike controlled rather than violent. And if you're unsure, don't cleave, choose sawing. In workshops, the brave decision is often the cautious one, because it preserves value for the later stages. Conventional sawing uses a thin rotating metal blade charged with diamond powder and lubricant. It removes material through abrasion, not through a slice like woodwork. This method gives you more freedom in where you place the cut, which is useful when cleaving directions don't match your plan, but you pay for that freedom. Sawing creates a curve, so there is inherent weight loss, and it takes time. Another important traditional concept is directionality. Diamond behaves differently depending on orientation, so sawing progress can change dramatically if the direction isn't favorable. The skill is steady, patient cutting, monitoring heat, lubrication, and blade condition, rather than pushing harder and hoping for speed. In many workshops, the quality of sawing depends heavily on the person setting the stone. The setter aligns the rough on the top so that the marked cutting line matches the blade path. This is precision work under magnification, and small errors become big problems later. A traditional best practice is to establish control early. Begin the cut carefully so the blade has a stable track, and don't rush the initial entry. If the stone is misaligned or the blade begins to wander, stop early and correct it, because late correction is usually impossible without serious loss. Think of saw setup like laying railway tracks. If the track is straight at the start, the rest of the journey is safer. If it's wrong, you'll derail. When sawing, pressure control is everything. Too much pressure can cause blade deflection, overheating, and chipping. Too little can waste time without real progress. Traditional operators often learn to listen to the saw. The sound and vibration tell you whether cutting is stable or struggling. Keep lubrication consistent to reduce heat and carry debris away. Also, check progress regularly rather than leaving the process unattended for long periods. The most dangerous moment is often near the end of a cut, when the remaining material is thin and vulnerable. Reduce force and stay attentive. Sawing rewards calm, repetitive control. If you find yourself becoming impatient, that's a sign to pause, not to push. Common sawing problems include wandering cuts, edge chipping, and excessive kerf loss. If a cut starts to drift, the worst response is to force it back while cutting. This usually makes the pass worse and increases damage. Traditional troubleshooting is stop, inspect alignment, and decide whether you can reset safely. Another loss control habit is planning for kerf from the beginning. You don't lose weight by accident if you accounted for it in the plan. Watch for overheating signs, because heat can lead to surface damage and later polish issues. Finally, keep your workspace clean. Grit from one stage can scratch surfaces in another stage, creating extra rework. Loss control is not one trick. It's dozens of small disciplines, repeated every day. Now we enter part 4, shaping. This is where the rough starts to look like a gemstone rather than a piece of crystal. In traditional practice, shaping means creating reliable geometry, a stable table reference, an outline that can support symmetry, and a girdle that won't cause setting problems later. Shaping is also where people accidentally lock in mistakes. If you shape an out-of-round girdle, you'll fight that problem through faceting. If you leave damage on the surface, you'll spend far longer polishing it out. So the goal here is not speed. It's creating clean, accurate foundations. Think of shaping as building the frame of a house. If the frame is square, everything else fits. Table smoothing in the early stages is really about creating a reference plane. Once you have a reasonably flat face, you can mount the stone more reliably, check alignment more accurately, and plan subsequent steps with less guesswork. Without a good reference, your angles can be false correct. They look fine on the tool, but the stone itself is not truly aligned. Traditional workshops treat reference faces as a checkpoint. Make a flat, inspect it, and only then proceed. The flat doesn't need final polish at this stage, but it should be stable, even, and free from deep scratches that could confuse later observation. In short, table smoothing is not cosmetic. It's the start of precision. Technique-wise, the main goal is to keep contact stable. Don't rock the stone and don't chase a flat by pressing harder. Hard pressure often creates uneven contact and deeper damage. Start gently, widen the contact gradually, and check frequently under magnification. Keep the working surface clean, because random grit can cut deep lines that later become stubborn polish marks. Also manage heat. Even without modern equipment, friction can create local stress or surface damage. The traditional approach is controlled repetition. Grind a little, check, adjust, and repeat. When you've done it well, the face looks uniform, and it behaves like a true plane when you test it against your positioning. That's the moment you can trust it as a reference. Bruting is the traditional process of forming the basic outline. Most commonly, the round girdle for a round brilliant. It usually happens in 2 phases. Pre-bruting is rough shaping, removing sharp corners and making the stone more manageable. It's about creating a workable form, not a final diameter. Final bruting is where you commit. You establish the intended outline, roundness, and general girdle thickness. The key traditional mistake is committing too early. If you final brute before you're certain of your plan and your reference phases, you lose flexibility. So in a disciplined workflow, pre-bruting creates options, and final bruting locks them in. You want to lock in the right thing once. Conventional bruting often uses diamond-on-diamond abrasion. One stone is rotated, and another diamond is brought into controlled contact to wear it into shape. It's a simple concept, but it demands control of pressure and contact point. If pressure is unstable, you can create uneven girdle thickness or introduce damage at the edge. A good traditional operator works gradually and checks often, because roundness errors grow quietly. Also, remember the purpose. You're not just making it round, you're preparing a girdle that supports symmetry, durability, and good setting later. So aim for evenness, not aggression. If you see strange surface texture developing, treat it as a warning. Better to slow down than to create damage that costs far more time later. The girdle is the widest part of the finished stone, and it affects almost everything: apparent size, symmetry, and setting security. Traditional control comes from frequent checks. Measure diameter in multiple directions, and don't assume that it looks round means it is round. Keep an eye on thickness too. A girdle that is too thin invites chipping. Too thick can waste weight and look clumsy. What you want is consistency. An even girdle that matches the intended proportions. One practical habit is to stop before you think you're done and do a full inspection. Most out-of-round stones happened because someone did one more pass without checking. In shaping, the last pass is often the most dangerous. A classic shaping defect is bearding. Tiny hairline fractures or a rough, fuzzy appearance around the girdle area. It's often caused by excessive pressure, unstable contact, or working in an unfavorable direction. The important thing is early recognition. If bearding develops and you ignore it, it can become a bigger removal problem later, costing weight and time. Traditional prevention is not complicated. Reduce pressure, stabilize contact, and keep the process smooth rather than jerky. Also, keep surfaces clean so you're not dragging grit across edges. If damage appears, pause and decide whether you can correct it with minimal material removal now, rather than hoping polishing will magically hide it later. Polishing doesn't fix structural damage. It reveals it only. Naturals are areas of original crystal surface left on the finished stone, often near the girdle. In traditional manufacturing, naturals can be a deliberate choice to preserve weight, especially when removing them would cost too much for too little visual improvement. But naturals must be managed intelligently. If a natural breaks the outline, disrupts symmetry, or creates an obvious flat spot, it becomes a quality issue. If it sits discreetly at the girdle and doesn't compromise durability, it may be acceptable in certain markets and grades. The key is intention. A natural should be a controlled compromise, not an accident, and always consider the setter. If a natural causes setting instability or concentrates stress, it's not worth the weight you saved. We now arrive at part 5, faceting and polishing, the stage everyone thinks of when they imagine diamond making. But in a traditional workshop, this is not where you create beauty from nothing. It's where you reveal beauty that your earlier steps made possible. Facetting is controlled geometry, angles, symmetry, and repeatability. Polishing is surface perfection, removing microscopic damage to allow light performance and clean refractions. Traditional work here depends on three things: a stable scaphe, accurate tang control, and reliable doping. It also depends on understanding directionality, why some facets polish quickly and others fight you. We'll go through the classic system, the workflow order, and the practical bench fixes that experienced cutters use every day. Traditional facetting relies on the simple but powerful system. The scaphe is the rotating polishing disc, usually metal, prepared with diamond powder and lubricant. The tang is the handpiece that controls angle and pressure, letting you bring a facet to the scaphe with repeatable positioning. The dop holds the stone, providing a reference so you can return to the same orientation again and again. The magic is not in any single tool, it's in repeatability. If you can return to the same position, you can maintain symmetry. This is why traditional cutters are almost obsessive about alignment and indexing. Every facet is a decision, but it's also a promise. I can match this facet on the opposite side. Without repeatability, that promise breaks. A scaphe isn't just spinning metal. It's a working surface with behavior. Traditional practice often uses different areas or rings for different purposes. A spot for testing contact, an area for steady cutting, and an area reserved for final polishing. Grooves and surface preparation help hold diamond powder and distribute lubricant. The other key issue is runout, wobble, or uneven rotation. If the scaphe isn't running true, you'll struggle to get perfectly flat facets, and polish will look uneven. So, a traditional cutter pays attention to scaphe condition like a chef cares about a sharp knife. Also, cleanliness is crucial. Contaminated powder or stray grit can create scratches that cost you far more time than the cleaning ever would. The scaphe sets the ceiling for your finish quality. Using the tang well is a blend of measurement and feel. Yes, you set angles, but you also control pressure and contact. Too much pressure can cause heat, drag lines, or facet distortion. Too little pressure can glaze the surface without polishing properly. You also have to avoid rocking. If you roll the stone even slightly, you round the facet or create uneven polish. Traditional cutters develop a steady touch, consistent approach, consistent pressure, and consistent time on the scaphe. It's also normal to make micro adjustments based on what you see. If a facet isn't meeting evenly, you stop and correct your setup rather than forcing it. The goal is simple to say and hard to do. Every facet should be flat, crisp at the edges, and matched to its pair across the stone. A classic traditional workflow is staged. In blocking, you establish the major crown and pavilion facets, the skeleton that controls proportions and symmetry. Then, in crossworking, you refine and bring those main facets into better alignment, checking midpoints and overall balance. Finally, in brillianteering, you add and polish the smaller facets, star facets, and girdle-related facets, bringing the stone to its complete pattern and sparkle. The key idea is order. Do not perfect tiny facets before your main geometry is correct. If the big structure is off, the small facets will only decorate a mistake. So the traditional discipline is: build the framework, confirm symmetry, then add detail. Think of it like tailoring. You fit the jacket first, and only then do you worry about the buttons. A very traditional, very real skill is transferring the stone from one daub position to another, especially when moving from pavilion work to crown work. This step decides whether your table ends up centered and whether the stone keeps its symmetry. The practical approach is to treat transfer as its own operation, not as a quick interruption. Align carefully, secure the stone without twist, and let the fixing fully set before you apply force on the scaf. After transfer, do a reality check. Are the key reference points still where you expect them? Collet alignment, girdle level, and the feel of the axis in the tank. If something is off, correct it immediately. Redoping early course minutes. Correcting misalignment late course waste, and sometimes the entire design. Polishing grain is one of the most traditional mysteries that becomes obvious once you've fought it. Some directions polish quickly and cleanly, others feel stubborn, draggy, and leave a hazy finish. This happens because diamond's resistance isn't identical in all directions. In practice, you detect grain by small tests, a light touch on a tiny area, watching how quickly it takes a shine and whether lines appear. If a facet won't polish, forcing it usually makes it worse. Traditional fixes include changing the polishing direction slightly, adjusting the angle minutely, reducing pressure, and ensuring the scaf surface and lubricant are correct. The point is not to memorize theory, it's to recognize the symptom and respond calmly. Grain is not your enemy, it's information. Traditional teaching often describes different planes, 2-point, 3-point, and 4-point, because they help you think about where polishing may be easier or harder. The practical takeaway is directionality. On some facet orientations, you have fewer friendly polishing directions, so control becomes more critical. When polishing fights you, you don't immediately blame the powder or your strength. You consider whether you're working in an unfavorable direction. Then you adjust, slight reorientation, slight angle change, lighter pressure, cleaner scaf, and a fresh approach. Over time, you develop a mental map, which facet types tend to behave well and which demand patience. This is why traditional cutters look so calm at the bench. They're not guessing. They're diagnosing. Directionality becomes a tool, not a frustration. We're now at the summary of the lecture. Traditional diamond manufacturing is a chain of small, disciplined choices. You don't save a diamond with a brilliant polish at the end. You protect its outcome by planning, preparation, controlled dividing, careful shaping, and then precise faceting and polishing. Let's quickly recap the main points, stage by stage, so you leave with a clear mental model of what matters most at the bench. Today we covered the traditional workshop route from rough to polished. We started with planning, reading the rough, balancing yield with risk, and using simple observation to make an executable plan. Then we moved into preparation, a clean bench, reliable hand tools, windowing for visibility, marking as clear instructions, and doping to establish a true axis. In dividing, we compared cleaving and conventional sawing, focusing on alignments, control force, and predictable loss control. In shaping, we built foundations, reference faces, girdle roundness, thickness, and the careful management of edge damage and naturals. Finally, in faceting and polishing, we covered the scathe dop system, stage facet sequencing, accurate transfer, and the practical handling of polishing grain and directionality. Thank you for joining me for this lecture on diamond manufacturing technology and skills. Goodbye, and see you next time.
Hello, everybody. I'm Liu Food. Welcome to join our course. Now let's come together to start our class. Welcome to this comprehensive course on gemstone manufacturing technology and skills. Over the following sessions, we will delve into the intricate art and precise science that transform raw stones into objects of beauty and value. We will explore the fundamental principles, diverse methods, and advanced technologies that define this skilled craft, from initial design to the final polished gem. Our curriculum is structured to guide you through the core domains of gemstone cutting. The content will be presented in 5 key sections. We begin with the processing of cabochon cuts, then move to faceted cuts, followed by beaded cuts, then explore fancy cuts, and finally examine the latest new technologies in gemstone processing. In our gemstone cutting course, we have already covered the preparatory work for gemstone processing, what equipment to use, how to design, and how to best showcase the beauty of gemstones. To maximize their value, this section will focus on the techniques of gemstone cutting. Dealing only with colored gemstones, diamonds and jade will not be discussed here. There is a wide variety of colored gemstones, and their cutting styles are equally diverse, based on the appearance and shape of contemporary colored gemstone styles. They can be divided into 4 main categories: cabochon, faceted, beaded, and fancy. We now commence the first course section of our curriculum, the art of processing cabochon gemstones. This style, characterized by a smooth, rounded, polished surface with no facets, is one of the oldest and most fundamental forms of gem cutting. We will explore its specific applications, often for opaque or translucent stones, or those displaying phenomena like cat's eyes or asters. A man detail the step-by-step techniques involved in transforming a piece of rough into a polished cabochon. The first section we will cover is the cutting of cabochon gemstones. This cutting style is also known by several other terms: simple face cut, oval face cut, convex cut, and so on. Its defining characteristic is that the gemstone has at least one curved, polished surface. This style is suitable for jade and some single crystal gemstones, particularly those exhibiting special optical phenomena. Many high-quality jadeite cabochons used in rings, as well as gems like cat's eye and star stones, are cut in this manner. Cabochon gemstone cuts can be categorized by their external appearance based on girdle shape and cross-sectional profile. According to girdle shape, they can be classified as round, oval, marquise, heart, briolet, rectangle, square, octagon, cushion, and freeform. Viewed from the longitudinal cross-section, common types of cabochon cuts include the following: single cabochon, characterized by one convex dome side and one flat side, suitable for various gemstone ring faces; double cabochon, characterized by 2 convex sides, with the upper dome being higher than the lower one, suitable for gemstone ring faces, exhibiting special optical phenomena such as cat's eye and star stones; lentil cabochon, characterized by 2 convex sides with arcs of equal height. This style is often used for opals. Hollow cabochon carbuncle, based on the single cabochon. A concave hollow is carved upwards from the bottom, suitable for gemstones with deep color and poor transparency, such as almandine garnet, commonly seen on the market today, as it can improve color by increasing transparency. Concave cabochon, based on the single cabochon. A concave hollow is carved downwards from the top, This allows for a more precious gemstone, that is, a diamond to be set within the hollow, such as setting a diamond into a chalcedony. Why are certain gemstones cut into a cabochon style? We must consider the following aspects. First is weight retention, to preserve the maximum possible weight of the finished gemstone. This is an important factor in determining the value of a cabochon-cut gem, especially for high-end gem varieties. Second, when a transparent gemstone has excessive flaw, such as inclusions, fractures, and so on, cutting it into a faceted style will reveal these defects. The cabochon cut, however, can effectively conceal these imperfections. I recall in 1996, I experimented by recutting several cabochon rubies that looked very clear and bright into faceted shapes. The result was that all the flaws within the stones became fully apparent in the finished pieces. Third, for opaque and translucent gemstones, the cabochon cut can excellently showcase the material's fine, smooth, and warm texture. Furthermore, gemstones exhibiting special optical phenomena are always cut into a cabochon style, such as those displaying cat's eye effect, asterism star effect, or agilurescence moonlight effect. These optical effects are related to the directional arrangement of internal inclusions or the gem structure and are only visible from specific orientations. Therefore, the design of such gemstones requires careful attention to orientation and positioning, which we will discuss in detail later. When presented with a piece of rough gemstone material, a craftsman will generally not begin work immediately. The first step is to carefully and comprehensively observe and analyze the rough. This involves identifying the gem species and thoroughly understanding the rough shape, weight, color, fissures, inclusions, transparency, and the presence of any special optical phenomena, as well as any major external flaws. For example, with a Sri Lankan sapphire, is the color even? For gems like emeralds and tourmalines, what is the extent of fissure development, the potential for certain stones to display special optical phenomena is a significant value-adding factor. When selecting a design plan for small pieces of rough, the processing design can directly reference standard style designs. For larger pieces of rough, there may be different design options for the same stone. The choice of which plan to use depends on which yields the highest value. Generally, gems exhibiting a cat's eye effect are cut into a high-domed cabochon, as this better showcases the effect, making the cat's eye line appear finer and brighter. Opals are often cut into a lentil cabochon, which relates to the typical shape of opal rough. Star rubies and sapphires are frequently cut as double cabochons, as this effectively displays the asterism while also retaining weight. Hollow cabochons are mostly used for gems like deep red almandine garnet, as this reduces color saturation, increasing apparent transparency and liveliness. The goal in selecting different cabochon cuts is to achieve the best possible visual effect and maximize economic value. For rough gemstones exhibiting special optical phenomena, positioning is crucial. Any rough stone containing paralleloline, needle-like or fibrous inclusions and be cut to display a cat's eye effect. This chatoyancy is only revealed with a cabochon cut, typically a single cabochon with a round or oval girdle. The orientation must ensure that the base of the cut is parallel to the direction of the needle-like or fibrous inclusions. If the gem outline is oval, the fibrous direction should be perpendicular to the gem's long axis. To make the cat's eye effect appear finer and more dynamic, the dome height can be appropriately increased. This greater curvature helps concentrate reflected light into a narrow band, forming a clear, bright, and lively cat's eye line. Asterism star effect can be considered a special manifestation of the cat's eye effect. The needle-like or fibrous inclusions are aligned along 2 or 3 directions, potentially forming a 4-ray or 6-ray star, as seen in star diopside or star sapphire. The positioning method involves aligning the base parallel to the plane containing the inclusions from all directions, that is, perpendicular to the z-axis. These two diagrams illustrate the orienting for cutting gemstones with cat's eye and star effects. In the chrysoberyl crystal, one set of needle-like or fibrous inclusions runs parallel to the crystal C-axis. Therefore, the base of the cut should be oriented parallel to these needle-like inclusions. In the ruby crystal, 3 sets of needle-like inclusions intersect on a plane perpendicular to the crystal's C-axis. Consequently, the girdle plane of the cut should be oriented parallel to this plane of intersecting inclusions. Agilurescence moonstone effect is an optical phenomenon caused by light reflection and scattering from lamellar twinning or interlayered structures of feldspar. With differing refractive indices, labradorescence effect results from interference caused by light reflecting off lamellar twin planes. Aventurescence effect is produced by the reflection of light from microscopically layered platy inclusions, although these 3 special optical phenomena differ slightly in their formation principles. They all belong to the category of effects that are only visible from specific orientations. Therefore, during orientation, the base of the cut should be positioned parallel to that specific direction. The range of materials commonly processed into cabochon-cut gemstones is extensive, covering almost all gem varieties except diamond. This cutting style is employed primarily to fully showcase the strengths of such materials, such as special optical effects, or to compensate for their shortcomings in areas like brilliance fire, transparency, and flaws. The processing technique is relatively straightforward, divided into several steps: sawing, blocking, girdling, doping, shaping, fine grinding, polishing, cleaning, and waxing. Having explored the world of curved and polished cabochon gemstones, we now turn our focus to the precise and brilliant art of faceted gemstone cutting. This fundamental category, defined by its intricate arrangements of flat, polished planes, is the quintessential choice for transparent stones, designed to manipulate light into displays of brightness, fire, and scintillation. In this section, we will delve into the detailed design principles, meticulous orientation requirements, and the exacting step-by-step processes that transform a crystal into a multifaceted jewel. In jewelry shops and jewelry advertisement videos, the most frequently seen gemstone style is still that of faceted cut gems set in pieces of jewelry. The faceted cut, also known as the prismatic cut or small facet cut, is characterized by the gemstone being composed of numerous small facets with specific geometric shapes, forming a regular 3-dimensional pattern. There are many styles of faceted gemstone cuts, with the 4 most basic categories being the round brilliant cut, the rose cut, the step cut, and the mix cut. Hundreds of derived styles have evolved from these for basic cuts. During processing, the number of facets and the angles need to be adjusted according to the specific gem variety, the reason being that different gemstones have different refractive indices. In principle, the faceted cut is suitable for all colorless and colored transparent gemstones. The design process for faceted gemstones is the same as for cabochon gemstones, similarly requiring steps such as determining the gem species, carefully observing the internal and external characteristics of the gemstone, analyzing the rough, and selecting a design plan. The overarching principle is that it must fully realize the gemstone's beauty, aesthetic form, textural beauty, optical beauty, and so on, and maximize its value. This determines the factors that must be considered during processing: weight retention, cutting angles and proportions, orientation of the cut, and flaw management. For gemstones of equal quality, greater weight equates to higher value. Therefore, weight retention is the foremost consideration during processing. The objective in gemstone design is to preserve the maximum possible weight of the raw material, or to yield a finished product that commands the highest market value. Processing methods: for smaller pieces of rough, the design should adapt to the natural shape of the material. The cut style should be chosen based on what the rough is best suited for, as this approach maximizes weight retention. For larger pieces of gem rough that require division in the cutting design, weight retention as to dimensions: the first is to endeavor to preserve largest possible weight in a single primary finished stone. The second is to strive for the maximum combined total weight of all finished stones produced from the rough, observing the three different division design plans for the same piece of gem rough presented in the course material. The leftmost plan employs a symmetrical division, which is most advantageous for weight retention and value enhancement. The central plan utilizes symmetrical division, which is the next best option. The rightmost plan applies equal division. Although this plan yields a greater number of stones, the weight is dispersed, material loss is high, and consequently, both the price per individual stone and the total overall value are significantly lower. The design principle for cutting angles and proportions is that the proportions and angles of the design cut should conform to the ideal facet-to-angle ratio. This aims to fully realize the aesthetic form of the faceted gemstone and exploit its specific optical effects. The optical effects displayed by faceted gemstones are primarily manifested in these three aspects: brightness, fire dispersion, and scintillation. Important considerations here are: first, most gemstones are colored, and their body color can mask fire. Second, most gemstones have a relatively low dispersion value, so fire is not prominently displayed. Third, colored gemstones should focus on leveraging their color advantage. Fourth, most colored gemstone rough lacks an ideal shape. Therefore, for colored gemstones, cutting angles and proportions should place greater emphasis on brightness and scintillation, exploiting color advantages and retaining weight. For colorless transparent gemstones with high dispersion, fire and brightness should be emphasized. For the orienting design of faceted gemstone cuts, the direction of the gem's table facet is generally used as the reference baseline. Several factors need to be considered, which can be categorized under the following circumstances. The primary consideration is for gemstones exhibiting distinct pleochroism, such as ruby, sapphire, chrysoberyl, tanzanite, tourmaline, and so forth. The guiding principle for designing such stones is to orient the best color direction as the table facet, while also considering the balance with weight retention. The second consideration for gemstones with strong birefringence. Certain gemstones, due to their high birefringence, can cause a noticeable doubling of facet junctions, particularly at the pavilion facets, creating visual confusion and detracting from the gem's beauty. An example is high zircon, birefringence 0.059. The guiding principle for processing such stones is to orient the gem's table facet as perpendicular as possible to the crystal's optic axis, as no birefringence occurs along the optic axis direction. For gemstones with uneven color distribution, such as color zoning, color patches, or color banding, for example, sapphire, tourmaline, amethyst, the processing principle is to orient the stone during cutting so that the colored area is positioned directly beneath the table facet and occupies the largest possible central region. Specific methods. For gemstones with color zoning, the direction of the zoning should be parallel to the table facet, and the area with the better color should be placed as low as possible in the pavilion, near the girdle, for example. As with amethyst, for gemstones with distinct color patches or concentrations, the better colored patch can be positioned in the pavilion, close to the culet. This allows internally reflected light to pass through the colored area, enhancing the overall color effect. Many gemstones possess cleavage, which is a property of gems. Gemstone cleavage can be categorized as perfect cleavage, distinct cleavage, imperfect cleavage, and poor or no cleavage. The impact of cleavage on gemstone processing is that polishing is difficult along the cleavage plane. Therefore, the principle for processing gemstones with cleavage is to avoid having any facet of a faceted gemstone, especially a table facet oriented parallel to the cleavage plane. For example, topaz has one direction of perfect cleavage parallel to the basal pinacoid. During design, the table facet should be oriented away from the cleavage plane, forming an angle of 5 to 20 degrees. Gemstones are natural products. During their formation through geological processes, they invariably bear the imprint of nature, various fissures, inclusions, and other imperfections, commonly referred to as flaws. These exist inside and on the surface of gemstones and can affect their beauty. A faceted cut is sensitive to flaws, as they can interfere with or obstruct the normal passage of light through the stone, impacting its appearance. Therefore, when selecting a cut style, obvious flaws should be avoided. For flaws that cannot be avoided, the principle is to retain the smaller ones and remove the larger ones. Retain those with less color contrast and remove those with greater contrast. Cracks must not be left inside the finished gemstone. For non-fracture flaws that cannot be avoided, they should be designed, as far as possible, into less critical positions in the finished gem, such as near the girdle area. The design of faceted gemstones is conducted into steps. Step 1. Examination of the rough gemstone material first. Identify and determine the gem species of the rough material. Then, observe its shape and record its weight, including the natural form of the rough, the shape of the usable portion, and the estimated weight of the finished product. Test the various optical and physical properties of the rough, including its color, color distribution, pleochroism, transparency, refractive index, birefringence, dispersion, optic axis direction, and the development and orientation of any cleavage. Carefully examine fissures and other flaws, including their size, direction of extension, depth, as well as the type, size, and quantity of imperfections. Methods of examination include immersion observation, spraying water onto the surface of the rough or immersing it in water for observation. Strong light illumination, using a focused flashlight or other strong light source to illumine it and examine the rough. Window cutting, for rough with an outer skin. A portion of the skin can be cut and polished away in an inconspicuous area to create a window. 4. Observation. Step 2. Determination of the design scheme based on the design principles outlined above. A design plan typically takes shape upon completion of the rough examination. When selecting a cutting style, priority is given to styles that are commonly used, traditional, or popular for that particular gem species. Styles most conducive to retaining the maximum weight of the finished product are also prioritized. For large, valuable gemstones, AI data simulation technology can be employed to assist in determining the design plane. The processing workflow for faceted gemstones consists of sawing, blocking, doping, girdling, grinding, and polishing. The sawing step is primarily intended for larger pieces of rough. For small stones, the process can proceed directly to the blocking stage. The grinding and polishing methods for the pavilion are the same as for the crown. These are repeated subsequent steps. Transitioning from the precise geometry of faceted stones, we now explore the realm of beaded gemstone processing. This style, defined by its simple, rounded forms, is a cornerstone of strung jewelry such as necklaces and bracelets, while geometrically less complex. Its beauty lies in the uniformity of individual beads and the overall color harmony of a complete strand. In this section, we will cover the typical materials used and detail the specific steps in the production workflow from initial slicing and dicing to tumbling, polishing, and drilling. Beaded gemstones have become very common in recent years, with an increasing number of people wearing beaded strands and necklaces. There is a wide variety of bead types processed, from mid to low-grade gemstones and jades, offering people more choices. Consequently, bead shapes have also become rich and diverse. The geometric form of the beaded cut is relatively simple, as beads are primarily used to make jewelry such as necklaces, bracelets, and pendants, requiring several, dozens, or even many to be strung together. The beauty displayed by beaded gemstones and jade lies not only in the shape of individual beads, but even more so in the color coordination and overall composition of the entire strand. These are the common processed bead styles found on the market. Based on their morphological characteristics, they can be classified into spherical beads, drum-shaped beads, cylindrical beads, and beads of other shapes. A wide range of materials can be processed into beaded gemstones, most of which belong to medium to low-grade gemstones and jades, such as turquoise, malachite, chalcedony, and tiger's eye. Some are also artificial materials like glass, plastic, and ceramic, of course. High-end materials like jadeite and nephrite are also used here. We might consider the currently abundant supply of synthetic diamond rough. High-pressure, high-temperature HPHT technology can produce synthetic diamond rough that is sufficiently large, especially pieces that are not of high clarity, since beaded gemstones are mostly used for necklaces, bracelets, and so on. This dictates that the beads must be of uniform size and produced in large quantities. Therefore, processing this style requires batch Mechanized production using equipment like multi-blade saws and chamfering machines to improve efficiency. However, this mass production also leads to significant material loss, making it unsuitable for processing precious gemstones. Consequently, beaded gemstones predominantly utilize inexpensive, low-grade gem materials. The processing of beaded gemstones, like other types of gemstones, involves several steps to transform a piece of material into a well-shaped, aesthetically pleasing spherical gem. This includes slicing, stripping, and dicing to cut the material into square forms, followed by procedures such as chamfering, coarse grinding, and fine grinding. Whether producing spheres or smaller beads, the material must go through the aforementioned processes to be crafted into a beaded form, with some steps encompassing several sub-procedures. The key difference in processing spheres versus beads lies in their size and production method. Spheres are generally larger and vary in individual diameter, typically requiring single unit processing. Beads, being smaller, are suited for batch, mechanized production. Additionally, when beads are used for strung jewelry, they require further steps, drilling and stringing. Some porous gemstones also undergo a waxing process. This is a set of equipment used in the processing workflow for small beaded gemstones. It includes a saw, cutting machine, a chamfering machine, a coarse grinding machine, a fine grinding machine, a polishing machine, and a drilling machine. Having examined the three primary, formally defined cutting styles, we now turn to the world of fancy-shaped gemstones. This category celebrates unorthodox forms, encompassing both deliberately carved freeform pieces and Baroque styles that follow the natural contour of the rough. This section will explore how these unique cuts maximize the use of material by adapting to a stone's inherent shape, unlocking creative potential beyond standard geometric patterns. Nature is variable, and the gemstones produced in the natural world are equally diverse. Not all gemstones that are mined can be processed into the styles we might desire. However, it is necessary to utilize mined gemstones as fully as possible. Therefore, some gemstone rough must be processed by adapting to the material's natural shape, which gives rise to the cutting of fancy-shaped gemstones. Fancy shapes can be categorized into two main styles, freeform and Baroque. Regardless of the style, the aim is to make optimal use of the mined gem material. The freeform style involves deliberately fashioning a shape based on the rough stone's natural form, color, and color distribution. Freeform cuts can be further divided, based on the tools and methods used, into freeform, faceted, and carved types. The Baroque style involved simply grinding and polishing the gem material according to the shape bestowed upon it by nature, smoothing edges and corners to complete the form. Among the processing of freeform gemstones, those cut into faceted styles are mostly high-grade gemstones, such as ruby and sapphire, during the processing of freeform faceted gemstones. Because the facets are numerous and irregular, it is essential to remember the angle and indexing position of each facet to ensure the subsequent polishing proceeds smoothly. Carving processing involves designing shapes based on the resemblance of the rough gem material to certain animals, plants, or other forms. In China, the primary material for carvings is jade, but gem crystals are also used, such as tourmaline crystals carved into Guanyin goddess of mercy figures, or quartz crystals carved into flowers. insects, and birds. Internationally, the craft of utilizing the geometric shapes and lines of various gem crystals for cutting and carving is known as gem carving or glyptics. This form of gem carving is very popular abroad and can frequently be seen at events like the Tucson Gem and Mineral Show in the USA, as exemplified by the work presented in the image on the right. The materials suitable for processing into Baroque free-form gemstones are not limited. High, medium, and low-grade materials and all be used. For instance, small pieces of jadeite material frequently appear in Baroque styles. This cut not only maximizes weight retention, but also fully leverages human imagination and makes the most efficient use of the material. The shape of a Baroque gemstone is essentially determined by the natural form of the rough. The process generally only involves smoothing the edges and corners and then polishing, making the technique relatively simple. Both grinding and polishing are typically completed using tumbling barrels, a method similar to that used for beaded gemstones, and it is widely applied in the processing of jadeite and other jades. The illustrated set of Baroque processed jadeite material, a set of turquoise Baroque pieces, and Baroque beads made from Haitian jade pebbles, largely represent the efficient utilization of mined materials, avoiding waste. Finally, we turn our attention to the forces shaping the future of our craft. This concluding section explores the revolutionary new technologies in gemstone processing, examining how innovations like laser cutting, 3D modeling, and intelligent automation are enhancing precision, efficiency, and creative possibilities in the industry. New technology is the core driving force behind the development of the gemstone industry. Laser cutting technology stands as a brilliant jewel in the crown of modern gemstone cutting. It employs a high-energy laser beam focused onto the gemstone's surface, instantly melting or vaporizing the material to achieve precise cutting. Its level of precision is astonishing, capable of accuracy down to the micrometer level, which is of extraordinary significance for processing minute and precious gem rough. For instance, when cutting tiny diamond melee for high-end jewelry settings, laser cutting machines ensure each diamond's facet is flat and smooth, maximizing the display of the diamond's brilliance and meet the stringent demands of the high-end jewelry market for ultimate craftsmanship. Furthermore, laser cutting is characterized by non-contact processing, effectively avoiding the physical pressure and damage to gemstones caused by mechanical cutting. This reduces the risk of flaws such as cracks and chipping in the gemstone, significantly improving the yield rate of finished products. 3D modeling technology, as the core tool of digital design, operates on the principle of using specialized computer-aided design (CAD) software based on a gemstone's physical and optical properties, combined with the designer's unbridled creative ideas. It constructs a three-dimensional virtual model of the gemstone jewelry. The designer becomes akin to a sculptor in a virtual world, able to freely manipulate every detail of the model within the software. Everything from the gemstone's cut and setting style to the overall form can be precisely controlled. Intelligent processing equipment is akin to an artisan endowed with superpowers, integrating a multitude of advanced technologies and possessing a high degree of automation and intelligence. Taking intelligent diamond cutting equipment as an example. Its internal high-precision CNC system acts as a shrewd brain. It can precisely control the cutting tool's path, speed, and depth of cut based on preset cutting plans. Through advanced sensor technology, The equipment perceives the diamond's hardness, crystal structure, and stress variations during the cutting process in real time. This information is swiftly fed back to the control system, which then intelligently adjusts the processing parameters. This ensures the cutting process consistently follows the optimal path, maximizing the diamond's brilliance and minimizing the rejection rate. The automated production line functions like a precisely orchestrated super machine, seamlessly linking each stage of gemstone processing to achieve efficient, uninterrupted flow from raw material to the finished product in an automated diamond polishing line. The rough stones first enter an intelligent sorting stage using high-precision optical inspection equipment and image recognition algorithms. Stones suitable for processing are rapidly screened and categorized by size and shape, then directed to different workstations. At the polishing station, multi-axis robotic arms precisely hold the diamond rough. Following pre-programmed instructions, they polish it on high-speed rotating laps from multiple angles and orientations, ensuring every facet is smooth, flat, and cut to precise angles. Subsequent steps such as polishing, final finishing, cleaning, and inspection are completed just as seamlessly, requiring minimal manual intervention and significantly shortening the production cycle. That concludes this part of the presentation. Now, let's take a break.
Welcome everyone. My name is Liang Wei Zhang. In this course, we will map how diamond and gemstone manufacturing has become a modern, data-driven production system. This session is deliberately balanced, roughly half on diamonds and half on colored stones, moissanite and jade-style products. Our core lens is technology, not gemology, scanning and planning, laser processing, automation, and the cluster economics that make scale possible. As you listen, keep one question in mind. What changed so that we can now manufacture with software-level repeatability? By the end, you should be able to describe a modern manufacturing line end-to-end and identify where yield, cycle time, and quality are won or lost. We will also use a standalone industry case from Wuzhou in Guangxi, including shipping jewelry as an automation scale example. During the course, I will build in clear transitions and summaries so you can follow the full logic without interruptions. Let's start with the big picture. Why modern manufacturing is a strategic shift, not just faster tools. When I say modern, I specifically mean measurable, programmable, and scalable, so decisions can be repeated across people, shifts, and sites. As we go, I will call out the practical control points you can audit in any factory: inputs, recipes, fixtures, and measurement loops. Here is today's map, and it is organized as two mirrors: diamonds first, and then gemstones and jade, with the same manufacturing logic. In the diamond half, we will touch scanning and planning only briefly, because you have seen serene-style workflows in the other diamond courses. Then, we will go deep on the laser transition, why lasers span direction constraints, raise yield, and enable integrated multi-operation machines. We will also cover automation on the polishing side, including laser cutting concepts and automatic final polishing. In the gemstone half, we will focus on how computer numerical control, CNC, automation, and synthetic diamond abrasives industrialize colored stones, moissanite, and jade products. Finally, we will move into a case module, Wuzhou as a global scale hub, and shipping as a practical example of automation at scale. Please treat this as a factory logic session. Every tool is evaluated by three key performance indicators: yield, throughput, and quality stability. With that frame, let's start with why modern manufacturing is not just a speed upgrade. Modern manufacturing is a strategic shift because it converts a craft sequence into a controllable system with feedback and repeatability. The first pillar is digitization. You capture the stone in 3 dimensions, model constraints and defects, and make a plan that machines can execute. The second pillar is lasers. You replace direction-limited sawing and cleavage decisions with programmable vectors and predictable curve control. The third pillar is automation. You reduce human variance in polishing, handling, and inspection, and you stabilize throughput at scale. The fourth pillar is integration. Tools alone do not win. The win comes from linking scanning, planning, marking, execution, and quality control, QC, data. Once you have this system, manufacturing starts to look like semiconductor-style process engineering: recipes, parameters, and statistical control. In diamonds, this mainly protects yield and value. In gemstones, this mainly unlocks extreme volume and consistent pricing. Now we can see why diamonds had hard limits under traditional processes. In systems terms, Modernization is the move from a wide, unstable process window to a narrow, controlled process window. That shift changes management. You invest less in heroic troubleshooting and more in standard work, statistical process control, SPC, and continuous improvement. Diamonds are mechanically extreme, but they are not uniform. Cleavage and polishing behavior depends on crystal orientation. Traditional processing therefore depended on choosing safe directions for cleaving, sawing, and polishing, and avoiding directions that increase risk. This creates two practical limits. First, geometric freedom is constrained by direction. Second, yield is sensitive to rough shape and defect placement. Because of those limits, expertise concentrated in skilled hands and tacit knowledge, and factories had trouble standardizing outcomes. Modern technology does not change diamond physics, but it changes what we can do within those physics by shifting work into planning and controlled machining. Scanning and planning reduce uncertainty by revealing inclusions and geometry before you commit to high-risk steps. Laser cutting reduces direction dependence by letting you remove material along programmable paths with tighter control of damage and curve. With those ideas, let's quickly recap the scanning and planning, and then move to lasers. A useful way to remember this is diamonds punish uncertainty because a single crack or burn can destroy most of the value. Therefore, modern factories design processes to reduce uncertainty early, before they commit to irreversible steps. This slide is the modern digital thread for diamonds. Scan, plan, mark, and then execute on machines with a traceable job file. Scanning captures three-dimension geometry and internal features, so the factory can quantify risk instead of guessing. Planning converts that scan into a target shape, a value/yield trade-off, and an executable set of operations and setups. Marking creates the physical link between software and stone, so the next machine step is aligned to the plan. Execution is then a controlled sequence: sawing or laser coating, bruting, table, crown, pavilion, and then polishing and inspection loops. The business value is not only accuracy, it is governance. You can compare planned versus actual, learn from defects, and reduce rework over time. This is the same logic that made modern manufacturing scalable in other industries. Design intent becomes a production recipe. Now, a brief inclusion mapping recap using Serene as a representative example. In many operations, this digital thread is implemented via an MES-style job traveler, so every station reads the same plan and writes back results. When you have that, process improvement becomes evidence-based. You can see which step creates which defect and fix the right lever. Inclusion mapping matters because the biggest yield losses in diamonds usually come from hidden risk, not from polishing skill. Serene's Galaxy family is one example of how factories industrialize this step. The machine builds a three-dimension model and maps internal features. The practical output is not the scan itself. It is a dataset that feeds planning software and downstream decisions. For our purpose today, remember 2 points. First, scanning reduces uncertainty. Second, it standardizes communication across teams and shifts. In a modern line, the scan becomes a file that can be archived, compared, and link it to process outcomes and defects. This is why scanning is the foundation for automation. Without a reliable digital input, automation will only amplify mistakes. Now we transition from seeing the stone to deciding what to do with it, which is the role of three-dimension planning. After planning, we will spend most of our time on the laser-enabled execution layer. In practice, factories also use scan archives to train planners and to benchmark the same rough type over time. So even though we are recapping briefly, remember, scanning is an enabler for both operational control and learning. Planning is where value is engineered, because it decides which material becomes finished facets and which becomes curve and dust. A modern planning tool converts the scan into a target shape and a sequence of operations, with constraints such as inclusions, symmetry, and risk rules. In practice, planning is also a business decision. You are trading yield, optical performance, time, and grading outcomes. The critical factory feature is handoff. The plan must be expressed in machine-readable terms, not only in a designer's intuition. That is why you see links from planning to marking, to machine setup, and eventually to automated polishing recipes. Another key point is traceability. When the plan is stored as data, you can compare plan versus actual and improve decisions with feedback. For this course, treat planning as the compiler that turns a three-dimension model into a production program. Now we move to the execution breakthrough, laser cutting. A good planning organization also defines do not cut rules, conditions where the safest business decision is to stop and reroute the stone. So planning is both optimization and risk policy, and modern factories formalize it as a set of rules and review steps. Laser processing is revolutionary in diamonds because it relaxes the direction, constraints that dominated traditional operations. In the traditional world, cleavage and polishing anisotropy forced you to choose directions carefully, and that limited geometry and increased risk. In the modern world, laser paths are software-defined, so you can approach the stone from the direction that best serves the plan. This does not mean anything is easy. It means the factory can control curve, minimize damage, and repeat a program reliably. The practical outcomes are higher yield, higher throughput, and stronger standardization, especially when handling and refixturing are reduced. Notice the shift in skills. The scarce skill moved from manual fill to process engineering, parameters, fixturing, and quality feedback. This shift also aligns with lab-grown diamonds, where batch characteristics reward standardized programs and automated cells. Next, we look at one representative laser approach, water-guided laser cutting and the Da Vinci-style automated cell. Laser cutting also supports fancy geometries and micro features because the tool paths can be engineered rather than implied by hand motion. But as always, the goal is not novelty. The goal is to expand the feasible space while keeping quality within a controlled window. Cinnova's laser microjet approach is useful to know because it illustrates how lasers are engineered to reduce heat and improve cut quality. The idea is to couple the laser into a thin water jet, which guides the beam and provides cooling and debris removal. In practical factory language, this is a way to get precision micro-machining while controlling thermal effects that can damage the stone. Da Vinci-style systems package cutting and shaping into an automated cell, which is where throughput and repeatability come from. From a process perspective, the important point is not the brand, it is the architecture. Controlled laser physics plus controlled fixturing and motion. When you combine that with good planning, you can move toward one setup, many operations, and reduce handling losses. If you are comparing laser platforms, look for evidence of a validated parameter window, cut quality, surface condition, and repeatability across lots. This is what separates a demo from production. Stable physics, stable fixturing, and stable maintenance routines. This is one of the building blocks for integrated workflows like the 4P concept that is now common in high-volume production syncing. Let's clarify 4P next, because it connects lasers to factory-scale productivity. In many factories, the next step after adopting lasers is integration, reducing separate stations and turning multiple steps into one controlled workflow. The 4P idea is a simple teaching model: girdle or bruting, then table, then crown, then pavilion. 4 major geometry steps for a round stone. Whether implemented as a single machine or a tightly linked cell, the goal is the same: fewer setups, fewer handoffs, and more predictable cycle time. This matters for lab-grown diamonds because standardized, rough and standardized designs make programs reusable and batch scheduling easier. Operationally, the biggest wins come from handling reduction and variance reduction, not from any single magic process parameter. In practice, you still need strong marking, fixturing, and measurement, or the integrated machine will simply integrate errors faster. Think of 4P as a direction for modern manufacturing. Process steps become modules, and modules become aligned with data feedback. Now we switch to another laser-enabled case study: laser faceting with Rattenkanti. Different vendors implement integration differently, so treat 4P as a mindset and an evaluation checklist, not as one fixed machine definition. Your diagnostic question is: how many times do we touch and realign the stone? And how much variance does each handoff introduce? Rattenkanti is a useful concept because it targets the highest volume part of the market, small stones, where cycle time and uniformity dominate. The basic idea is to use a laser to create facets, reducing the dependence on purely mechanical polishing for every surface. In high-volume environments, even a modest reduction in polishing time per stone can translate into major throughput gains at factory scale. However, laser faceting only works as a system. You need stable starting geometry, strict marking, and consistent fixturing and transfer. The production question is not, can the laser cut a facet? The question is, can the factory repeat this for thousands of stones with low defect rates? This is why we talk about parameters, recipes, and measurements, not only about the machine. On the next slides, I will translate the concept into shop floor implications. What changes and what you must control. Keep the KPI lens: yield, throughput, and quality stability. In small stones, the economics are unforgiving, so machines must be designed for fast cycles, easy fixturing, and minimal manual touch time. That is why laser faceting is discussed together with throughput engineering and system discipline, not as a standalone trick. In the shop floor, Rattenkanti-style laser faceting changes the sequence and the critical control points. First, fixturing becomes a first-class process. If the stone is not held and indexed consistently, the laser's precision is wasted. Second, marking and alignment become repeatable operations because the laser program assumes a known coordinate system. Third, the production team must manage parameters, power, speed, and patterns as recipes that are validated and logged for a given product. Fourth, inspection shifts from artisanal visual checks to faster metrology loops that decide rework quickly. The benefit is speed and standardization, but the risk is also system-wide. A wrong recipe can create a wrong batch very efficiently. So the correct mental model is laser plus fixtures plus QC loop, not laser alone. Next, we connect this to throughput thinking and integration. A practical best practice is to define a golden sample and log recipes around it, so drift is detected early. This is where SPC thinking helps. You do not wait for visible defects. You watch leading indicators like power drift and fixture wear. Throughput thinking means you design the whole line so that no single station creates bottlenecks or unstable queues. With laser faceting, the upstream planning and marking discipline must match the downstream machine speed, or you will simply move the bottleneck. In high-volume small stones, the real metric is not peak speed. It is stable yield per hour with low rework. This is where batch rules matter. How many stones per lot, how you label, how you route rework, and how you prevent mixing. It is also where data matters. If you cannot attribute defects to a recipe, a fixture, or a lot, you cannot improve the process scientifically. So, when you evaluate any laser system, ask, what is the recipe governance and what is the closed-loop measurement plan? This is the same evaluation logic we will use for polishing automation next. Let's transition to automation on the scale side, using Vajramani as a concept reference. When throughput is the target, it is useful to speak in overall equipment effectiveness OEE's terms, availability, performance, and quality as separate levers. Their language forces the team to ask whether losses are due to downtime, speed loss, or defect-driven rework. Vajramani-style systems represent the push to automate blocking and polishing steps that historically depended on highly skilled operators. The concept is to standardize motion, pressure, and sequences so that the scale process becomes more repeatable across shifts and factories. From a factory management view, this is about variance, reducing the spread of outcomes so grading and rework become predictable. Automation also supports training. Instead of teaching a craft from scratch, you teach operators to run a controlled process and handle exceptions. However, scale automation does not remove the need for process knowledge. It requires even tighter control of consumables, calibration, and maintenance. In other words, automation trades labor skill for engineering skill and discipline. When you combine automation with digital planning, you get a clearer plan to execute to measure loop, which is the basis for continuous improvement. Next, we look at another polishing automation layer, the lead automatic final polishing, which targets consistent finish. In the long run, automation reduces dependence on the small number of top artisans, which lowers operational risk and stabilizes delivery. At the same time, it raises the importance of maintenance, because uptime is the currency that pays for the automation investment. Dialect GEM3003SED is a good example of how factories standardize the last mile polishing step. Final polish is where small variations still matter, because they affect surface finish, midpoints, and ultimately grading outcomes. Automatic polishing machines try to control pressure and sequence consistently, while adding safety features like error detection and backup power. In practice, the KPI to watch is repolish rate, how often stone must go back, and how much time is lost to correction. As with other automation, results depend on inputs, blocking quality, stone preform consistency, and consumable condition. Therefore, the implementation question is, what is the calibration routine, and what data is captured for quality feedback? When these machines are connected to planning and QC, the factory can begin to run polishing like a controlled process, not a craft. Now we assemble everything into an end-to-end diamond production line blueprint. For evaluation, ask for before and after data on surface finish defects and repolish minutes per stone, not only nominal machine speed. The most mature factories treat final polish as a controlled finishing step with documented checks, not as a last-minute rescue. This blueprint is a reference model you can use to evaluate any modern diamond factory, regardless of which brands of equipment it uses. The flow starts with intake and identification, because traceability is the backbone for learning and for consistent customer outcomes. Then scanning and planning create the executable job file, and marking creates the physical alignment between file and stone. Next comes cutting or multi-operation machining, where lasers and integrated workflows can reduce handling and improve repeatability. After that, polishing and QC close the loop, because inspection is where you decide, accept, rework, or scrap, and where data is captured. The management levers are the same everywhere: yield control, throughput control, quality control, and data discipline. Notice how this model treats machines as parts of a system. Every handoff is designed, not improvised. If you use this blueprint as an audit tool, you can ask one question per stage. What is the input spec? What is the recipe? And what is the measurement? Those three questions, input, recipe, measurement, are a simple way to diagnose why one factory is stable and another is unstable. Before we complete the diamond half, we now watch two videos. One is about a laser facetting machine. The other one is the first automated full facetting laser system for diamonds. And then switch to gemstones and jade, where the same logic drives even larger scale. For our first case study video, we shift from general factory automation to a dedicated laser facetting solution. The video introduces a machine built to deliver fine, repeatable facet geometry across round and fancy shapes, supporting both symmetrical and asymmetrical cutting. It is offered with green or IR, infrared radiation, laser configurations, and can be set up for 8 or 16 facets per side, allowing manufacturers to match production speed with cut complexity. As you watch, focus on how digital parameters are translated into physical facets, and where the process gains consistency compared with manual faceting. We frame this case study around Cinnova's Da Vinci Diamond Factory, a system designed to compress the rough-to-polished workflow into a highly automated, data-driven sequence. The rough is first scanned and planned, then the machining recipe is transferred to a 5-axis CNC platform that combines a high-power green laser with laser microjet, a water jet-guided laser. This water guidance cools the diamond during ablation, helps reduce cracking risk, and support tight, parallel curves for precise geometry. An integrated breakthrough detection function recognizes cut completion and automatically triggers facet changes, enabling efficient multi-facet production in one run. Now we switch to gemstones and jade-type products, where equipment modernization produced a dramatic industrial leap. In many segments, the limiting factor was not material physics like diamond cleavage, but the ability to standardize shapes, angles, and surface quality at volume. This is why CNC, automation, and synthetic diamonds abrasives had such a visible impact. We will first explain the drivers, then look at modern faceting cells and consumables, and then move to jade carving and moissanite style small stone production. After that, we will enter our stand-alone case, Guangxi Wuzhou and Xiping jewelry, which shows what happens when a full ecosystem and a high-volume product meet. Please keep the same KPI lens, yield, throughput, and quality stability. But note that in gemstones, throughput often dominates the business model. Let's start with why modernization was so fast in this field. As we move into gemstones, note that product categories are broader, so standardization often happens by narrowing SKUs and tightening tolerances. This is also why hubs matter. They can specialize by product type and build deep know-how in a narrow set of geometries. Gemstone processing modernized quickly because three levers improved at the same time: equipment capability, consumables quality, and industrial clustering. On the equipment side, CNC fixed-sitting and programmable indexing made angle control and repeatability much easier than purely manual methods. On the consumables side, synthetic diamond abrasives became widely available, consistent in grit and cost-effective, which stabilized surface quality. On the clustering side, once a hub forms, suppliers, technicians, training, and repair services concentrate, and know-how diffuses rapidly. When these three levers move together, the whole system jumps. Factories can run multiple machines per operator and deliver consistent products. This is why certain hubs can dominate global supply in specific categories of artificial gems or processed stones. Next, we look at the equipment layer more concretely, starting with the fast-sitting cell. A simple signal that modernization is happening is when you see processes described in recipes and batches, not only in artisan terms. Another signal is measurement. As soon as factories can measure quickly, they can scale because they can separate good, rework, and scrap fast. This slide contrasts the classic fixed-sitting machine mindset with the modern CNC cell mindset. In the classic setup, skill sits in the operator's hands. Indexing, angle setting, pressure control, and the rhythm of cutting and polishing. In the modern cell, skill moves into programs and fixtures. The same design is executed repeatedly with controlled angles and consistent sequences. That enables batch production. You can run a queue of identical stones, measure results, and tune one recipe instead of relearning every time. CNC does not remove craftsmanship. It changes where craftsmanship lives, into design libraries, tooling choices, and process tuning. In practice, modernization means more stations become standardized. Preforming, facetting, polishing, and sorting can be organized as a cell. To make this industrial, you still need a strong consumables and process control, which is our next slide. Even if a shop does not own full CNC, it can still modernize by standardizing angle libraries, fixtures, and inspection, which reduces variance sharply. So think of CNC as the visible tip, but standard work and measurement are the foundation underneath. When people say a gemstone factory is industrial, they often mean the consumables and process control are engineered, not improvised. The consumables include labs, plated tools, loose diamond powder with batch control, coolants, and stable dopes and fixtures. The process control includes calibration routines, standard tolerances, sampling rules, rework gates, and tool wear tracking. These two are what turn a CNC machine into a production system, because they stabilize inputs and therefore stabilize outputs. The instructor noble here is simple. A great machine cannot compensate for unstable inputs, and modernization fails if consumables and QC are neglected. If you want a quick diagnostic, ask for their calibration schedule, their consumables replacement rules, and their defect taxonomy. Now we apply the same logic to a different product family, jade and hard stone carving. In well-run factories, consumables management is treated as part of intellectual property, IP, because it encodes how the factory achieves both speed and finish. So modernization here is not glamorous, but it is decisive. Disciplined tool and consumable control often beats a newer machine with poor discipline. J processing illustrates a different side of modernization, not facetting, but carving and turning of complex shapes. CNC carving can produce repeatable relief patterns for pendants and decorative pieces, with consistent depth and surface treatment paths. CNC turning enables batch production of bangles, beads, and tubular forms by controlling diameter, thickness, and concentricity. As with facetting, digitization is the unlock. One computer CAD model becomes a repeatable program and a product line. The operational challenge is finishing. Roughing is easy, but achieving a premium surface finish requires toolpath design and controlled polishing steps. Therefore, factories often combine CNC machining with standardized polishing workflows and inspection criteria. Next, we move to moissanite and synthetic gems, where modernization is extreme because volume is extreme. Digitization also enables mass customization. Once designs are in CAD, small variations can become new SKUs with minimal extra engineering. This is why carving and turning businesses often behave like design-driven manufacturing, not only like raw material trading. Moissanite and other synthetic small stones behave like industrial products, standard materials, standard designs, and extreme volumes. In such settings, the winning model is not one artisan per stone, but many machines per operator, guided by programs and rapid QC. Local reporting from Wuzhou highlights signals like multi-stage CNC cutting machines, CNC grinding sets, and the use of AI sorting and inspection. The manufacturing logic is the same as earlier slides. Stable inputs, stable recipes, and fast measurement loops to keep rework low. Environmental systems also become part of modernization, such as wastewater recycling and dust control, because volume makes these constraints real. For teaching purposes, treat moissanite as the clearest example of how gemstone processing becomes factory manufacturing. Now we are ready for the case module, Wuzhou and Xiping, where this industrial logic is visible at city scale. Because moissanite is manufactured, not mined, supply is more predictable, and that predictability supports long-term automation planning. So this segment often becomes an early adopter of AI sorting, inline inspection, and standardized high-volume cells. This section is a standalone industry case module, designed so you can reuse these slides independently. We will first frame Wuzhou as a cluster, scale, specialization, and why automation investment makes economic sense there. Then we will highlight Xiping Jewelry as an anchor enterprise, using reported workshop metrics to illustrate automation at scale. We will also provide a workflow template and an automation economics lens you can apply to any factory tour video. Let's begin with Wuzhou at a glance. The key is to keep the story structured. Cluster scale, anchor enterprise, workflow, economics, and then video evidence. Wuzhou is important for modern gemstone processing because it demonstrates how a cluster can reach global scale output and therefore justify large automation factories. China's Central Television (CCTV) reporting has highlighted scale signals such as a very large share of global artificial gems and very high annual processing and trading volume. Those numbers matter because they imply stable demand, stable product categories, and the ability to amortize equipment and process engineering costs. Clusters also reduce friction. Suppliers, technicians, repair services, and training pipelines concentrate locally, which reduces downtime and speeds learning. In other words, Wuzhou is not just a location, it is an operating system for gemstone manufacturing. With that context, we can understand why a single enterprise can build very large automated workshops and still run them profitably. Next, we move from the cluster level to one anchor example, shipping jewelry. In clusters, the hidden advantage is coordination. Standards spread, equipment vendors adapt to local needs, and throughput becomes a shared capability. So when you assess a hub, assess not only factories, but also the surrounding supplier and service infrastructure. Local reporting about shipping jewelry highlights a classic scale automation pattern: large floor area, dense machines, and very high daily output. The reported workshop configuration emphasizes a single large polishing floor, hundreds of automated polishing sets, and a throughput narrative measured in millions. From a teaching standpoint, we treat these as signals of a standardized product mix and a highly engineered operating rhythm. The factory logic is that automation converts scale into unit cost advantage, but only if uptime and variance are controlled. That is why the teaching point on this slide stresses ecosystem conditions: stable stock keeping units, SKU, reliable consumables, and dense service support. If those conditions hold, the enterprise can safely raise the automation ratio and keep a lean operator to machine structure. We can think of the large polishing floor as a polishing farm, where the management challenge is scheduling, maintenance, and defect containment. That is exactly why governance matters. Labels, batch rules, and QC gates are what keep high-speed automation from turning small errors into large losses. This workflow is intentionally generic, so we can apply it to Wuzhou, shipping, or any other modern gemstone factory. It starts with raw material and preforming, because stable starting geometry is a prerequisite for automated downstream steps. Cutting then becomes a program operation, where cooling, dust control, and fixture repeatability determine both speed and defect rate. Polishing follows as an automated or semi-automated sequence, ideally with in-process checks to catch deviations early. Sorting and QC are where industrial scale is made possible. Optical measurement and AI vision can classify millions of stones quickly. Finally, packing and traceability prevent mixing, manage rework, and protect customer trust. Next, we quantify the economics. Why automation makes sense when a cluster supplies volume and services. We should observe not only machines, but also screens, parameter panels, and QC stations, because that is where modern becomes visible. Also capture material flow, bins, labels, and rework routing, because that is how factories protect stability at scale. In a gemstone hub, automation economics are driven by three practical realities: volume, learning speed, and shared services. Volume makes fixed costs affordable. Machines, tooling, and process engineers can be amortized across massive output. Learning speed improves because many similar factories face the same problems, so solutions spread quickly through technicians and suppliers. Shared services reduce downtime. When repair parts, calibration skills, and consumables are local, machines stay running. In this environment, The key KPI is uptime. A high automation ratio only pays if overall equipment effectiveness stays high. Quality stability is the second KPI, because stable quality prevents rework from destroying throughput advantages. Therefore, hubs like Wuzhou are not only competitive because of low labor, they are competitive because of system-level productivity. A simple unit cost breakdown is depreciation per stone, consumables per stone, labor per stone, and rework loss per stone. Automation mainly reduces labor per stone and rework loss per stone, but only if the process window is controlled and uptime stays high. Now please watch two videos. I will first play this video on the left. Everyone will see using laser cutting technology to do preform cutting on gemstone materials. Precise, efficient, and with low loss. Then, we will play this video on the right. We can see that the robotic arm follows the program that has been written in advance, step by step pressing the gemstone rough onto the grinding wheel for polishing. And it will also adjust the angle according to the designed process requirements. We will again watch two videos that are both about modernized processing of moissanite. This video on the left, edited from two self-media videos, describes the whole process of moissanite, from plate cutting to loose stone grinding. Everyone first comes to understand an overview of the moissanite processing process. In order to let everyone understand in detail the specific process of large-scale grinding, I have arranged a zoom-in short segment of the batch grinding procedure. Hope that you can have the experience through the video.
搬时翻过来继续磨面，磨面，磨好了再检查一遍。
这个外面是粗膜，里面那个黄色盘子是在抛光，它这个角度是可以不停的调整的。
就这一套。
This video clip on the right is filmed from a modernized moissanite processing factory. Everyone can quickly and intuitively understand the large-scale processing and production process of moissanite.
先沾上胶粉，然后过到这边沾上宝石，送到这边磨面部，在这反过来，再送到这边磨底部，磨好就回到这里脱胶。这些就是磨好的石头，让他们从这里列队，滴滴滴滴滴滴排队站好。 挨个拍照检验身材如何，然后这上面就 AI 自动识别等级，好的在这儿，差的在这儿。
Now we again take a look at modernized processing technology for jade and jadeite. The video that is played first is filmed by me in a Chinese jade processing factory. It uses modernized high-pressure water flow plus garnet powder to impact the jade, achieving the purpose of quickly and safely cutting the jade according to an almost as you wish shape. Next, the video that will be played uses the laser to cut open the jade. This is also a modernized method. Okay, we again take a look at jade carving. This video on the left, we will see that the designer only needs in computer software to design the specific pattern well. The data is transmitted to the engraving machine, and then it can carve out exquisite patterns. And the video on the right then is the 5-axis engraving machine that is now relatively popular in China. It can, through 3-dimension scanning or CAD software design, establish 3-dimensional graphics and then output to the 3-dimension engraving machine to carve out jade works precisely and quickly.
给它一个数码图，它就能够雕出来，标准化的。
自动换刀5到6秒完成，毫米级精度雕完免修，效率翻倍不费工，新手也能快速上手，解锁传统工艺达不到的精致质感。
大5轴雕刻机，精度高，效率快，480度旋转无死角，最大可雕1米大件，成品光滑不手修，玉石、金属、木头统统能雕。工厂、工作室、学校赶紧安排。
5轴联动，直接开挂，雕玉石、刻金属、漏木塑，雕钻角度一键拿捏， 零死角狂甩传统机床10条街，精度细到毫米级，复杂曲面咔咔成型，效率飙到飞起，同行看了都惊掉下巴。搞雕刻没他真的亏到哭。
有没有一个想法？因为工艺太复杂，一直留在电脑里。5轴雕刻就是把你最天马行空的设计稳稳的变成现实，复杂曲面一次搞定，智能加工就是这么省心。别让工艺限制了你的想象力。
After watching these 2 videos, has everyone gained a fresher understanding of modern jade carving? In the industry, there are also people who put forward such a thought. A master's work, is it not very easily able to be replicated by modern processing technology? And what do you think? This convergence slide is the bridge between the 2 halves of the course. Diamonds and gemstones differ in material physics and value density, but their factories increasingly share a common technology stack. Both sides now depend on data capture, computer-aided design, CAD, or computer-aided manufacturing, CAM, planning, programmable execution, metrology and QC, and analytics. In diamonds, the stack protects high value and high yield. In gemstones, the stack enables extreme volume and stable product uniformity. This convergence is why skills in process engineering, automation integration, and data governance are now transferable across segments. So, when you invest in learning modern manufacturing logic, you are not learning one niche. You are learning an industry-wide capability. Next, we end with a forward view, where the industry is going in the next 3 to 5 years. This is also why vendors increasingly offer integrated software plus machine packages. Customers want outcomes, not isolated tools. So the strategic question becomes, how well does the stack integrate? And how fast can the factory learn and improve with data? Looking forward, 3 trends are strengthening across diamonds and gemstones: digital twins, AI planning, and deeper factory automation. Digital twins mean a full 3-dimension representation of the stone and the process, allowing simulation of yield, cost, and risk before cutting. AI planning means better cut decisions and earlier defect risk prediction, so factories waste less material and time. Factory automation means more robotic handling, more inline measurement, and more data-driven maintenance to protect uptime. These trends reinforce each other. Better planning makes automation safer, and better automation generates cleaner data for planning. For managers, the key capability becomes integration, connecting tools into a reliable line with governance and continuous improvement. For instructors and learners, the takeaway is that modern manufacturing is a moving target, and the mindset matters more than any single device. With that, we conclude with a short set of key takeaways. Sustainability pressure will also rise, especially for high-volume gemstone hubs. Energy, water, and waste handling become competitive factors. So the future factory is not only automated, it is also audited, measured, and optimized for resource efficiency. Here are the 4 takeaways I want you to live with. First, modern manufacturing is a system. Data, machines, QC, and standard work must be designed together. Second, lasers change feasible geometry and reduce direction constraints, while automation changes feasible scale and stabilizes outcomes. Third, clusters like Wuzhou accelerate learning and make large automation investments economically viable through services and volume. Fourth, the winning capability is process engineering and integration, because brands of machines change faster than manufacturing logic. Thank you, and this concludes the session. If you want to go deeper after this lecture, The natural next session is to workshop a real production line and define its recipes and measurement plan. That exercise makes the technology practical because it turns concepts into a checklist you can use in your own operations. Thank you for your attention. See you next time.